Third Law of Thermodynamics. The third law was developed by a German chemist, Walther Nernst, during the years 1906 to 12. That's why third law often referred to as Nernst's theorem, or Nernst's postulate. His formulation of the Nernst heat theorem helped pave the way for the third law of thermodynamics, for which he won the 1920 Nobel Prize in Chemistry. He is also known for developing the Nernst equation in 1887. According to third law of thermodynamics, the entropy of a system, at absolute zero, is a well-defined constant. Or in other words, the entropy of a perfect crystal at absolute zero, is exactly equal to zero. But what is entropy, and what is absolute zero? Entropy is a measure of disorder in the universe. An object or substance which is highly disordered will have high entropy. For example, when you put things in order, you are decreasing the entropy. Now, how about absolute zero? Absolute zero is defined as negative 273.15 degrees Celsius, or 0 Kelvin, which is known as the coolest temperature. Hence, if we combine the definition of entropy and absolute zero, this is how third law of thermodynamics works. Assume this cube is a rigid, isolated system, and the spheres are atoms in that system. At high temperature, the atoms have high kinetic energy, and moves erratically, thus, having a high entropy. As temperature drops, the atoms loses kinetic energy and the entropy of the system decreases. At 0 Kelvin, atoms with perfect crystal structure will stop moving and zero entropy is achieved. For imperfect crystals, the entropy will drop, but not to zero. The reason why imperfect crystal will never achieve a zero entropy is because the imperfections in the structure carries energy, which in hand gives more possible microstates. Hence, the entropy will be a constant non-zero value. The equation for the third law of thermodynamics is given as S equals to Kb multiplied by logarithm of W. A microstate is the possible configurations of molecules, atoms, or ions at any given instant. At absolute zero, or 0 Kelvin, for a perfect crystalline structure, the entropy will be zero, because there is only one possible microstate. S equals to Kb logarithm 1. Since log 1 is 0. Hence, the entropy, S, will be 0. Any imperfections in the crystalline structure will causes the entropy to be a non-zero constant, as degeneracy is present. This is why third law of thermodynamics states that the entropy of a perfect crystal, at absolute zero, is exactly equal to zero. Now, let's have a look on the example of third law of thermodynamics. We will be calculating this example using MATLAB. First, all the given variables are listed down. Using the information given, assuming the gas is ideal, we can find the number of moles by using the ideal gas formula. The number of moles is found to be 1.443. Next, we want to find the change in internal energy using delta U equals Q plus W. However, since there is no change in volume, work done by the system is equals to zero. Therefore, the change in internal energy is equal to the heat transferred to the gas, which is 15,000 joules. Next, we can find the final temperature, T2, by using the formula Q equals to N times CV times T2 minus T1. Rearranging the equation and substituting the value, we'll get T2 equals to 1000 Kelvin, now that we have all the values required. We can find the change of entropy using the formula stated on the MATLAB. We equate P2 over P1 to T2 over T1 because the process is adiabatic. The entropy change is found to be 20.7944 joule per Kelvin. For question B, since change of state of the gas is same as part A, the change of entropy of the universe is equal to the change of entropy of the system, which is 20.7944 joule per Kelvin, making the stirring process irreversible. Thanks for watching.